Sangeeta is currently a senior lecturer at the Department of Chemistry, Anna University, Chennai. She has completed her PhD in the field of polymer chemistry from the University of Madras in the year 2000 and has teaching and research experience of more than 10 years. Her research interests are in the following fields: fuel cells for clean energy, functional membranes for desalination, and polymers for biomedical applications. She has published more than 20 research articles in national and international journals and has more than 40 research articles in national and international proceedings. Presently, she is guiding 6 research scholars for their doctoral degree.
Welcome to UGC lecture series on the subject of polymer science. Today in Unit 3, Lecture 3 regarding the characterization and analysis of polymers, we are going to discuss about exclusively the thermal properties of polymers. Thermal properties or the thermal behavior of polymers are very important to be learned because of the fact that any particular polymer is being used for particular application will have to serve over a range of temperature. So what happens to the mechanical properties or the strength or whatever it is when it is subjected to the thermal effect will have to be understood before a particular polymer is taken for an application. Today in this lecture we will be doing with the introduction to thermal properties of polymers. A little bit of introduction have been already covered in the earlier classes, wherein we have spoken about the basic difference between thermoplastics and thermoset polymers. And today, because we are learning about the characterization and analytical methods in this Unit 3, we will be focusing on the determination of a specific property which is very important in case of polymers, namely the glass transition temperature, as well the melting point if it is available with a suitable polymer. So here we will be concentrating about what a glass transition temperature of a polymer is, what is melting point, and how these values are determined, or the thermal properties of a polymer is studied or analyzed by making use of various techniques, most importantly the dilatometer, thermomechanical analyzer, differential scanning calorimetry shortly called as DSC, thermogravimetric analyzer, and the dynamic mechanical analyzer. These are the 4 or 5 different important equipments that are basically used to study the thermal behavior of the polymers. Basically, we call the thermal behavior in terms of what is called transitions. Transitions in polymers are supposed to be those different changes that happen in a polymer sample when they are subjected to the temperature or thermal effect. The temperature below which a particular polymer is in a glassy state and above which it is rubbery in nature is called the glass transition temperature. Almost all the polymers, they have this glass transition temperature below which they are hard and strong, above which it becomes flexible in nature. Hence, Tg is very important for a particular polymer so that that particular polymer can serve its application well below its Tg or well above its Tg depending upon the property that is required for that use. Hence, Tg is very important, and it is also important to know about Tg in order to process a particular polymer. If we are interested in processing a particular polymer, to obtain a particular shape, it will have to be subject to the thermal effect. How much amount of temperature is required or how long the temperature of the material has to be taken for the polymer to be shaped in a particular form, that is determined by what is called this Tg. So, not only for the service life but also for the processing temperature, glass transition temperature becomes very important for a particular polymer to be known or analyzed by making use of these techniques. Basically, the transitions in polymers are of 2 types. You call them as molecular motions of the polymer chains. How do they take place? They take place in terms of what is called first order transition, which is determined by the melting point, and the glass transition temperature, which is supposed to be called as the second order transition. Therefore, as we have seen in the conventional materials, you have only one order transition, but in the case of polymers, you have what is called the melting point as well as the glass transition temperature. Both of them, they are with respect to first and second order transitional behavior that happens with respect to the movement of the polymer chains in a particular sample. Further, this first order transition, which is represented by melting point, could compose of two different types of motions which are named over here, and the second order transition represented by glass transition temperature may also involve two other types of motions. Therefore, there are four possible motions that can happen in a polymer sample. The first order transition includes translational motion of the entire polymer molecules, which make the whole of the polymer to move easily, which permits the polymer to flow easily. So, this translational movement of the entire polymer chain is called the first type of first order transition. The other type of first order transition is that it can also possess a flexible movement of the segments. Certain portion of the polymer segments can be subjected to the flexible movement. For example, some 30 to 50 carbon atoms in length, which are present mostly or generally in the main chain, which allows a polymer to have a little better flexible movement of the polymer chain. These two types of transitions can be accommodated as the first order transition, which is represented by what is called the melting point or TM temperature. Hence, the TM or the melting point involves change in phase, that is from the solid to the liquid phase, that there is a change in the phase. That is what is accommodated in the first order transition. Whereas, the polymers are also characterized by the second order transition represented by Tg value, wherein you have two other types of movements. The first one is a movement of very few atoms along the main chain or the side groups. It could be few atoms, 4 to 10 atoms or so, which makes the polymer to have a little bit of flexibility, but at the same time it doesn't flow entirely. So, such a type of short flexibility that is possible in a polymer paves way for this glass transition temperature or a second order transition to happen in the polymer sample. The other form of motion could be due to the vibration of the different atoms that are present along the polymer chain with respect to their equilibrium position. When they are available at a particular position, they take up their equilibrium position. If there is a possibility for the atoms to vibrate up and down slightly above or below, or they come out of the equilibrium position, such a type of movement can also be called as a second order transition. These two types of smaller movements are called second order and the major movements are called the first order transition. Any polymer is supposed to have definitely mostly the Tg values. Sometimes it may also possess the Tm value depending on the amorphous and crystalline region that are present in a particular polymer. Let us have a brief introduction to these types of Tg and Tm that are possible in the polymers materials. Coming to the second order transition, which is more specific to the polymers, glass transition temperature, which we have seen already, is that particular temperature at which there is sufficient amount of energy available for the motion of the secondary transition. So, when does a second order transition take place? When there is sufficient or adequate amount of energy that is possessed by the atoms or the molecules of the polymers are available, then they can see the secondary transition. If more amount of energy is available, they can undergo what is called the first order transition or the melting transition. Now, we should make a note that Tg is not a phase transition at all. There is no change in the phase. The polymer material remains solid, but it becomes more viscoelastic and flexible at Tg than below Tg, where it was stronger and harder and brittle. At the same time, Tm does have a phase transition, that is from the solid to the liquid phase. Now, this particular diagram represents the different types of temperatures that are possible along the polymer materials. All polymers are characterized by a specific Tg. At the same time, we should make a note of the point that it may not have a particular value for the Tg. It could have a range of Tg value because of the very basic obvious reason or the very basic nature of the polymer, that they have a diverse characters because of the presence of the high molecular weight as well the different types of groups that could be attached to the polymers. So, they are basically characterized by a Tg value which need not be very sharp. It could be a range of temperature value, but this value is well below, much below the melting point or the first order transition. You can classify the different states of the material, a polymer material, as glassy state, rubbery state or viscoelastic state, and the liquid state. When the temperature is increased from one point to the other side, what happens is the glassy state of the polymer, which is a brittle plastic, when it touches the glass transition temperature, becomes flexible, rubbery, and a tough rubber and plastic material is obtained. Further, when the temperature is increased beyond Tg, there is a temperature Tm that is reached, where there is a transition from this rubbery state to the liquid state, where there is a phase transition. Now you call the polymer as a polymer melt. So, you have a brittle plastic, you have a rubbery viscoelastic plastic, and then a liquid melt of the same polymer at 3 different areas over the temperature range. The first temperature achieved, you call it as Tg, and then you call the phase transition as Tm. Now, let us get into the differences between the glass transition and the melting point of a polymer sample. Glass transition temperature, or Tg, it is basically a property of amorphous region in the polymer, whereas Tm, a sharp melting point, is basically a property of the crystalline region. And we know very well that the polymer consists of both amorphous as well as crystalline region. But when you have a more crystalline polymer, it may show a sharper Tm value and does not show a Tg value at all. Similarly, when you have a more amorphous polymer, it will show a Tg value. At the same time, it may not show the melting point at all. Such cases are possible, but generally polymers are semi-crystalline in nature. They have both amorphous as well as crystalline region. Hence, they could be characterized by having both Tm as well as Tg values. Tg, below glass transition temperature, the polymer is disordered, amorphous, solid with some amount of immobile molecules that are present as the polymer chains. Below Tg, they are immobile in nature, whereas above Tg, it is the same polymer which has got disordered, amorphous, solid, which has slight mobility that is possible in the system. When you talk about melting point, below the melting point, polymer is having an ordered crystalline solid, and above the Tm temperature, it is disordered melt. So, this is the basic difference between Tg and Tm in a particular polymer, and hence Tg is also called as the second order transition and the Tm is called the first ordered transition. Tg. When an amorphous polymer is heated, the temperature at which it changes from glassy to rubbery state is called Tg. A given polymer do not have a unique value of Tg, it could have a range of value for the glass transition temperature. Of course, the measured values of Tg by different methods may depend on primarily these factors, and other factors could also play a role. Primarily, molecular weight of the polymer, thermal history of the material and its age, the method of measurement that is used to determine the Tg value, and also the rate of heating and cooling. Generally, all the measuring methods, they involve the increase in the temperature and subject the material to the thermal effect, and then study how the Tg and Tm and Tc values are happening in the polymer. Now, when the temperature is increased, the rate of heating, or when the temperature is decreased, the rate of cooling also does play a role in determining the values of the Tg and Tm in the polymer. This particular chart gives an idea about the various possible Tg values of polymers. Take the case of polyethylene. Polyethylene, again you have LDPE, LLDPE, HDPE and so on. For a low density polyethylene, the value lies at around minus 125 degrees Celsius, whereas a polypropylene sample atactic structure may have minus 20 degrees Celsius. Polyvinyl acetate, which is another plastic or polymer, has got a 28 degrees Celsius, whereas PV has got 81 degrees Celsius. Now you could see the difference here. This has got a minus value, whereas these materials have got a positive value. Above this temperature, these polymers are supposed to be a plastic in nature, supposed to be flexible, can be accommodated for various possible changes because of the minimal movement of the chains. Whereas in the case of polyvinyl acetate, PVC and all, at room temperature or at below temperature, they behave like a brittle material which may break down when they are subjected to a mechanical stress. Polyvinyl alcohol has a TG value of 85 degrees Celsius. Polyvinyl chloride isotactic structure has 100 degrees Celsius. Polystyrene is another aromatic polymer which has got a TG value of 100. Polymethyl methacrylate, the value lies between 80 and 110 degrees Celsius. Polyurethane, which is supposed to be a flexible polymer due to the presence of the ether linkage, which is nothing but NHCOO. This OO ether linkages gives flexibility to the polymer, and hence the TG value is much lower when compared to the other plastic materials. Polyethylene terephthalate, which is another PET material used for commercial applications, has got a TG value of 69 degrees Celsius. Let us have a short break. Welcome back after the short break. The relation between TG and TM can be generalized by this particular slide. For symmetrical polymers, generally the TG value is almost half of the melting temperature. Suppose the melting temperature is 200, it is almost 100 the TG value is. Whereas in case of unsymmetrical polymers, it is about 2/3 of the melting point. The TG value is 2/3 of the melting point. So in general, we can normalize the equation like this. The TG by TM ratio varies between the values of half and 2/3. Now, the TG and TM values of different polymers. Let us talk about a crystalline first order transition and then amorphous polymer which has got a more second order transition. In the case of crystalline polymers, if you try to draw a graph between the change in the volume and the temperature, there is a shift in the nature of the polymer at a particular temperature called the melting point, where the crystalline solid gets converted to the liquid melt. So you could see here there is no volume change at all at this particular region because that is consumed. The amount of energy that is going into the system has been consumed for the phase change, and there is no change in the volume. It abruptly goes into this form and then it retains there for some time and then it becomes a polymer liquid melt. So this is characterized by what is called the melting point in the case of crystalline polymers. Whereas the graph is different in the case of amorphous polymers, where you find the glass transition temperature and not the TM value. Here, when the temperature increases, there is a change in the volume of the polymer. You could identify this glass transition temperature. From the glassy state, it gets converted to the rubbery state, and there is a typical mark which is seen by this particular graph which indicates the TG value. In general, you may have both crystalline region as well as amorphous region, which could be characterized by the presence of both TG as well as TM in many of the polymers you could see. Now, the glass transition temperature of polymers is basically a function of chain flexibility. Different polymers have different segments on their backbones. The ease of movement of such segments basically depends on the chemical structure and also the physical environment that is present. Movement of such segments require kinetic energy. Different polymers have different amount of energy that is required for them for the mobility to happen. Below TG, these polymer segments do not possess sufficient amount of energy to move. Hence, when a stress is applied on such polymers, the polymer may not be able to move to its newer position in order to relieve the stress, whereas above Tg they become flexible and start moving. One point which has to be noted here is glass transition temperature is a property of amorphous polymers or amorphous regions of the semicrystalline polymers and not crystalline polymers. Now, let us move on to the determination of glass transition or melting point of different polymers. There are several methods that are used to determine the Tg values. One very simple laboratory based method is dilatometry. Dilatometer is basically an instrument that is placed in a thermostat bath, wherein you make use of a silicon oil in the measuring jar, and then you put the polymer sample and then increase the temperature. Now, the silicon oil do not show much change in volume when there is a thermal event that is taking place. Hence, whenever there is an increase in temperature, the polymer sample which has been added to the system shows a volume expansion, and the increase in the rise in the silicon oil which could be seen through the capillary tube is only due to the expansion of the polymer and not to the expansion of the silicon oil. So, hence the dilatometer equipment or the instrument, a small glass apparatus, paves way to determine the different volume change that is happening when the polymer is subjected to the thermal effect. So, when you try to measure the different temperatures and the change in volume, mark a plot, then you could see that the temperature increases, there is not much volume change of the polymer, but at the place of glass transition temperature, there is a rapid increase in the volume change. This is basically due to the reason that polymer molecular chains have undergone a second order transition and the chain flexibility or movement has got initiated, which is indicated by this temperature. The specific volume and the density of silicon oil which is used for the experiment does not change much with temperature. That is why it is generally used, and on heating the silicon oil level rises in the capillary tube, which is only due to the expansion of the polymer and nothing else due to. Hence, the experiment becomes very simple, very useful, very laborious, a laboratory based method wherein you can immediately determine the range of Tg of the polymer where it is taking place in that material. Other sophisticated methods would include TMA, DSE and so on. TMA is another important method where again you measure the expansion or the change in dimension of the polymer when they are subjected to the thermal effect. TMA stands for thermomechanical analysis. Here the basic difference between the previous dilatometer and this is, in this case you make use of the expansion. In the earlier case it was the volume that was measured, in this case it is a dimensional change that is measured. Anyway, both of them are with respect to the temperature increase. Now, when the temperature increases, expansion of the polymer is not seen initially, but when there is a Tg value that is crossed, you could see there is a rapid increase in the dimension of the polymer, which is indicated by this turning point of the curve. This could be easily identified as the glass transition temperature. Thermomechanical analysis measurements record the changes that are caused by the changes in the free volume of the polymer. The increase in the free volume is caused by increased energy absorbed in the chains, which allows the movement of the chain to occur, and this is indicated by the change in the length or breadth or whatever it is, dimensional changes occurring in the material, which is what is measured in the TMA method. Now, let us move on to the DSC. Differential scanning calorimeter is a very important method which is very frequently used to determine the Tg values of polymers. Here the DSC measures the heat flow difference between the sample and the reference. In this particular experiment, you have a sample where the polymer sample is placed and you have a reference area where a reference material is placed. What basically happens is, with the increase in the temperature, the various possible endothermic events and exothermic events that are taking place with respect to the polymer sample is measured. The basic principle of the instrument is that there is no change in the temperature of the sample and the reference. If an endothermic process is happening in the polymer sample, the amount of energy that is required flows into the sample. If it is an exothermic process that happens at that particular temperature, it gives out or releases out the heat that is compensated with the help of the reference. So, basically the temperature is maintained and the amount of heat evolved out or absorbed during the different thermal events, whether it is endothermic or exothermic, are taken care or measured, which is called as the DSC response in the y axis. So, when you try to plot this response, DSC response with respect to temperature, a curve like this is basically obtained for any polymer sample. This side you know the different peaks that are obtained on the other side. On the upper side you call them as endothermic peaks, and those which appear at the bottom we call them as exothermic peaks. Glass transition is basically an endothermic process, and hence there is a positive deviation in the endothermic side, which is recognized at a much below temperature. When you cross this temperature, a baseline is always available. When you cross this Tg temperature, it further prolongs depending on the characteristics and the thermal capacity of the material. They may undergo what is called the Tc or crystallization temperature, which is indicated by an exothermic peak, which can further be followed by an endothermic peak if the polymer is undergoing a melting process, which is further increased with the increase in the further temperature. It may go up to 700 to 800 degrees Celsius. The curve still further goes, and at a point you can reach even the degradation of the polymer taking place at a particular temperature, which is again indicated by the positive slope, that is endothermic slope. Some polymers, before getting degradation, they may also undergo oxidation, due to which the exothermic peak can also be seen in the curve. So, the basic idea is all these different changes, variations in the peak lines, that is in your baseline changes, are indicated by various possible thermal events that are occurring at the various temperatures of the polymers. The first positive endothermic peak indicates the Tg, and then the exothermic peak by crystallization temperature, and further endothermic is melting, and this could be followed by degradation or oxidation of the sample. Easily all these events can be identified by making use of this differential scanning calorimetric technique. Differential scanning calorimetric technique is basically called as a quantitative technique because of the reason that it is used to measure the heat flow which provides enthalpy changes which happens in the polymer sample during a particular thermal event. Hence, it is possible to calculate the area that is below or above the peaks, that is your curves, and that is exactly the measurement of the enthalpy or the amount of heat that is required for that particular change to take place, or the amount of heat that is released out during that particular event. Hence, DSC is not only useful to determine the glass transition temperature and other thermal events that are possible in a polymer, a general thermal behavior of the polymer could be analyzed, and also the enthalpy changes can also be measured, which makes the tool as a quantitative tool in addition to the qualitative tool when a particular thermal event is happening in the polymer. Other than these basic methods, there are also other thermal methods like DMA and other methods which we will see in the later classes. So, in summary today, in today's class we have seen about the transitions in polymers, what is Tg and Tm of polymers, how do we determine the Tg value by making use of various techniques like dilatometry, thermomechanical analysis and differential scanning calorimeter. Of course, we will be doing with the dynamic mechanical analysis method and the thermogrammetric analysis, which are also very useful tool to determine the thermal properties of polymers in the next class. Here are few questions. What is Tg? What is a dilatometer? What is measured in a thermomechanical analyzer? How DSC is useful in analyzing a polymer sample? What are first order and second order transitions? Thank you.